Thanks for watching this lecture on the use of macro balances for scaling up and down. A semi-fundamental approach to scaling up and scaling down is regime analysis, which is based on skilled balance equations. Making balances is bookkeeping for process engineers. As we already saw in the first lecture, balance equations include an accumulation term and terms for all relevant transport and reaction mechanisms. In this course module, you will learn how to scale a process balance and how to obtain characteristic times for each sub-process. The characteristic times tell you which sub-processes is the bottleneck for each skill. If different skills lead to different bottlenecks, there's a scale-up issue. Let's start with a simple balance of the amount of dissolved oxygen in an ideally mixed batch bioreactor. There's no conversion and only aeration, which results in oxygen transfer from the gas to the liquid phase. The balance only has an accumulation term and a transfer term. And this balance can be analytically solved to get the oxygen concentration as an exponential function of time. The constant in the exponent, minus KLA, determines the rate of change of this process. The inverse of this constant is called the characteristic time and has the units of second. A large KLA corresponds to a short characteristic time and thus a fast process, here the blue line. A small KLA corresponds to a long characteristic time and thus a slow process, here the black line. The steps to take in the scale-up-down approach are the following. First, set up the proper balances for all relevant species, chemical compounds, as well as heat and momentum, and for each phase in which they appear. Include in each balance the relevant mechanisms acting on the species, which can be conversion, transport, or transfer. Do not solve the balances, but scale them. Identify all characteristic times and analyze their scale dependency. Then determine the dominant mechanisms for the process at each scale. To illustrate this approach, we again consider the balance of dissolved oxygen in the liquid phase, but now for a continuous process in a bioreactor with oxygen uptake, a liquid flow into as well as out of the reactor, and supply of oxygen by air sparging as well as surface aeration. Well, we can set up a balance for the oxygen in the liquid phase with an accumulation term and 5 terms for the mechanisms acting on the amount of oxygen. This is step 1 of the proposed approach. In the second step, we scale the balance such that each term has a unit of 1 per second. In our example of the oxygen balance, we do so by dividing each term by the same amount of oxygen. The amount of oxygen by which we divide is chosen such that each term between brackets is within an order of magnitude from 1. In our example, we can divide by the amount of oxygen that is present in the bioreactor when it is saturated with oxygen at fermentation conditions. And this is indicated as O2 star. When we do so, we obtain a scaled balance in which the rate of change of the scaled amount of oxygen is the sum of the rate capacities of all the mechanisms, which are the inverse characteristic times, multiplied by terms of the order 1. Now we can identify the 5 rate capacities, or the inverse characteristic times, of our example, namely the reaction, the liquid flow in, the liquid flow out, the oxygen transfer from the bubbles to the broth, and finally, the surface aeration. We can write each mechanism as a function of the operational settings, transfer coefficients, and geometries of our bioreactor system. Let's take one term as an example. The transfer of oxygen from the bubbles to the liquid has a rate capacity that is a function of the oxygen transfer coefficient KL, the bubble diameter dB, and the total gas and liquid volumes, VQ respectively VL. We see only one transport mechanism in which the dimension h appears, so this one is scale dependent. Notice that this sometimes depends on the assumptions made. In our example, the flow in and flow out are scale independent because we assume that the liquid residence time is kept constant across the scales. The conversion rate is weakly scale dependent because the oxygen concentration in the bubbles usually changes with scale as well. The oxygen transfer from the bubbles has the weakest skill dependency in this example. Then the fourth and final step of our approach, that is to identify the dominant mechanisms on each skill. We need to fill in some actual values to do so. Note that the equilibrium concentration of oxygen at the interface of the bubbles is skill dependent, due to a different oxygen depletion of the gas phase and the hydrostatic pressure on both skills. After filling in all the known values for the two different skills in our example, we see that the reaction rate and the oxygen transfer from bubble to the broth are the dominant, that is, the fastest sub-process in our bioreactor on both skills. We also see that the skill dependency of the surface aeration. So what can we learn from the values found at the two skills? Well, first of all, we observe that not all terms are identical on both skills. So there's no full similarity and the oxygen concentration is skill dependent. However, we see that of the two dominant mechanisms, one is weakly and one is hardly skill dependent if the equilibrium oxygen concentration and the KLB are kept similar when scaling up or down. Only one sub-process strongly depends on the skill, so near similarity is possible. Thirdly, it's possible that scaling up or down leads to a regime change. This means that at a different skill, different mechanisms are dominant. This happens, for example, when scaling down to a microreactor, where surface aeration dominates over oxygen transfer from the bubbles. We will return once more to the full oxygen balance for the ideally stirred continuous bioreactor. By rearranging the terms, we can express the accumulation term of the ratio C over C star as a sum of a constant part and a part that depends on C over C star. The steady state solution of this equation, that is when the accumulation term equals 0, strongly depends on the rate capacities of the two dominant mechanisms, of which the skilled reaction rate is skill dependent, albeit weakly. In other words, a different steady state oxygen concentration can be expected on both skills. The overall inverse characteristic time of the transfer processes is the sum of the inverse characteristic times of the oxygen transfer from the bubbles, the outflow, and the surface aeration. This overall characteristic time, and thereby the process dynamics, is dominated by the skill-independent mechanism, bubble aeration, in this example. The example of oxygen balance of a bioreactor illustrates how carefully setting up a balance, proper scaling and analysis of the skill dependency of the resulting characteristic times forms a not too complex but very insightful approach to rationally scaling up and down. I hope to see you back in the next module.